Hello, in this video we're going through the OCR A-Level Chemistry 2023 Paper 3, Unified Chemistry, question by question. I'll show you not just the answers, but how to think through them in the way the mark scheme expects, so you know exactly how to pick up marks in the exam. If you can, pause and try each question before watching the explanation. That's where the real learning happens. I've included a link to my website in the pinned comment. If you're looking for a chemistry tutor and would like some extra support with your studies, feel free to take a look. Let's get started. Question 1 is about the first 36 elements in the periodic table, and these are provided in a table. We need to refer to these 36 elements only and write the symbols that fit the description. In question A, we are asked by the three elements that, when in a molecule, can form hydrogen bonds with other suitable molecules. These elements are nitrogen, oxygen, and fluorine, as hydrogen bonding only occurs when hydrogen is covalently bonded to any of these three atoms. A hydrogen bond is an attraction between a hydrogen atom bonded to nitrogen, oxygen, or fluorine, which gives the hydrogen a strong partial positive charge, and a lone pair of electrons on nitrogen, oxygen, or fluorine in a nearby molecule. There are some exam traps on this question, the carbon and the chlorine. The carbon is not electronegative enough and the carbon-hydrogen bonds do not form hydrogen bonds. Chlorine is electronegative, but it's larger and has a lower charge density, so hydrogen bonding is not normally considered. Instead, HCl shows permanent dipole-dipole interactions. In Part B, we are given the successive ionization energies of an element in period 2. Here, we are not looking at the values themselves, we are looking at the difference between each consecutive value. If we compare these differences, we can see that the biggest jump occurs between the 6th and 7th ionization energies. What does this tell us? It tells us that after removing 6 electrons, the next electron is being removed from an inner shell, much closer to the nucleus. Because it's closer to the nucleus, much more energy is needed to remove it. This means the atom has 6 electrons in its outer shell. And in period 2, the element with 6 outer shell electrons is oxygen. In Part C, we are asked to identify an element that is a solid at room temperature and pressure, and that has a simple molecular lattice structure. So, let's look at our options from the periodic table provided. First, we rule out gases and liquids. We can ignore elements like oxygen, nitrogen, and chlorine because they are gases at room temperature. We also ignore bromine because it is a liquid. We can also ignore metals like iron or copper as they are metallic structures. Finally, we can rule out giant structures in elements like carbon and silicon. So, we are left out with phosphorus and sulfur. The marking scheme also accepts selenium or arsenic. Solid phosphorus exists as molecules formed by 4 atoms bonded together. Solid sulfur exists as molecules formed by 8 atoms. You could argue about the selenium and arsenic and they are acceptable answers as well. If it was my exam, I would stick with the clear winners, phosphorus and sulfur. In question D, we are asked to identify the 2 elements with atoms containing 5 unpaired electrons. Electrons fill orbitals singly before pairing up. In the s subshell, we have only 1 orbital, giving only 1 unpair electrons. In the p subshell we have 3 orbitals, that gives a maximum of 3 unpaired electrons. In the d subshell we have 5 orbitals, giving a maximum of 5 unpaired electrons. Therefore, we need to focus on the transition metals, D block. The first one is manganese, Mn. Its configuration is argon core, for S2, 3d5. 5 d electrons, each in its own orbital, all unpaired. This is a straightforward answer. The second one is chromium, Cr. Chromium is an exception. Instead of going for S2, 3d4, it promotes 1 electron from the 4s into the 3d to get a half-filled d subshell, which is more stable. So, its actual configuration is argon core for S132. Chromium technically has 6 unpaired electrons in total, 1 in 4s and 5 in 3d. But the question asks which elements have 5 unpaired electrons. Out of all the elements given, only chromium and manganese have 5 or more, the rest have fewer. Therefore, the answer is chromium and manganese. In question E, we are asked by the element in period 3 that exists in the solid state as a network of atoms bonded by strong covalent bonds. As we have seen in question C, silicon forms a giant networks of atoms bonded together. In part F, we are asked to identify the p-block element in period 3 that forms a compound with fluorine with octahedral molecules. The elements in the p-block and period 3 are aluminium, silicon, phosphorus, sulfur and chlorine. An octahedron looks like 2 square-based pyramids glued together at their bottoms. An octahedral molecule is a shape where one central atom is holding onto 6 other atoms. To hold onto 6 fluorine atoms, the central element needs to have enough electrons to share. Sulfur has 6 outer electrons. It can share all 6 of those electrons with 6 fluorine atoms to form a sulfur hexafluoride, the most famous example of an octahedral molecule. So the answer is sulfur. In question G, we are asked for the element that forms 1 negative ions most readily. To form a 1 negative ion, the element needs to gain 1 electron. Halogens gain 1 electron easily to achieve a full outer shell. As the reactivity of the halogens increases as we move up in the periodic table, the fluorine is the most reactive of the group. Therefore, the answer is fluorine. In question H, we are asked by the element with an average atomic mass of 1.2 for 4 times to the power of minus 22 grams. If we multiply this number by the Avogadro number, we get a value of 74.9. Looking to the periodic table from the data sheet, we find that this value corresponds to arsenic. The answer is arsenic. Question 2 covers topics from several areas of chemistry. Part A focuses on 2 rubidium salts, RbClO3 and RbClO4. The first question tells us that chlorine has a different oxidation number in each salt and asks us to name the compound RbClO4. At first glance, you might assume that chlorine has an oxidation number of -1, since that is often the case in compounds such as sodium chloride. However, chlorine can have a range of oxidation numbers, including positive values when it is bonded to oxygen. To determine the oxidation number of chlorine in RbClO4, we need to consider the oxidation numbers of the other elements. Oxygen usually has an oxidation number of -2. The main exceptions are peroxides and compounds containing fluorine. Since there are 4 oxygen atoms, their total contribution is 4 multiplied by -2, which gives -8. Rubidium is a group 1 metal, so it has an oxidation number of +1. Because RbClO4 is a neutral compound, the sum of all oxidation numbers must equal 0. The oxygen atoms contribute -8, and the rubidium contributes +1, giving a total of -7. Therefore, chlorine must have an oxidation number of +7 to balance the overall charge. When chlorine forms arccyanions, the systematic epoch names are based on the oxidation number of chlorine, which is written using Roman numerals. You may have come across the traditional names hypochlorite, chlorite, chlorate, and perchlorate. Although these names are still widely used in chemistry, they are not accepted by the OCR specification for naming questions, so it is safer to use the systematic names in the exam. Since chlorine has an oxidation number of +7 in RbClO4, the correct name is rubidium chlorate 7. In the second question of question 2a, we have that a student carries out an experiment to determine the enthalpy change of solution of rubidium chloride 5 using the following method. A 2 grams of solid rubidium chloride 5 is added to water in a well-insulated container. The initial temperature is 23.0 degrees Celsius. The mixture is stirred until all the rubidium chloride 5 has dissolved. The final temperature is 21.5 degrees Celsius. The final solution has a mass of 102 grams. We are asked to determine the enthalpy change of solution of rubidium chlorate 5 in kilojoules per mole. Assume that the specific heat capacity of the solution is the same as that of pure water. This value is given in the provided data sheet for the exam. The enthalpy change of solution is the heat energy change when 1 mole of a substance dissolves in excess solvent under standard conditions. Be careful with the sign of the enthalpy change. If heat is released, the process is exothermic, so the enthalpy change is negative. If heat is absorbed, the process is endothermic, so the enthalpy change is positive. In this example, the temperature decreases. A decrease in temperature means heat has been absorbed, so the enthalpy change will be positive. I will write the positive sign now so that I do not forget it later. The heat energy change can be calculated using this equation, Q equals mc delta T. This means we multiply the mass of the solution by the specific heat capacity and by the temperature change. Before substituting the values into the equation, we should check that all the units are consistent. The specific heat capacity is given in joules, but the final answer is required in kilojoules, so we must convert the result from joules to kilojoules at the end. The mass is given in grams, which is correct because the specific heat capacity is also based on grams. The temperature change is measured in degrees Celsius, while specific heat capacity is expressed using Kelvin. However, because we are calculating a change in temperature, a change of 1 degree Celsius is the same as a change of 1 Kelvin, so the units are consistent. The temperature change is calculated by subtracting 21.5 degrees Celsius from 23 degrees Celsius, giving a temperature decrease of 1.5 degrees Celsius. There are 2 masses mentioned here. The first is the 2 grams of salt. The second is the 102 grams of solution. Since we are calculating the enthalpy change of the solution, we must use the mass of the solution, which is 102 grams. Substituting the values into the equation, the heat change is equal to 102 multiplied by 4.18 multiplied by 1.5. This gives 639.5 for joules. Converting to kilojoules gives 0.6395 for kilojoules. These kilojoules come from 2 grams of rubidium chlorate 5, but we need the energy value per mole. Since the relative formula mass of rubidium chlorate is 169 grams per mole, we can calculate the energy change as 54.0 for 113 kilojoules per mole. Rounded to 2 decimal places, this gives 54.0 for kilojoules per mole. Don't forget the positive sign. In Part B of Question 2, we have that a student investigates the rate of a reaction that is first order with respect to hydrochloric acid. The student carries out a reaction using 0.680 moles cubic decimeter of hydrochloric acid. The initial rate is 9.52 times 10 to the power of -4 moles per cubic decimeter and second. Then, the student dilutes a different sample of the same acid with water. The pH of the diluted acid is 1.50. The student repeats the reaction using the same volume of this diluted acid. We are asked to determine the initial rate using this diluted acid. Because hydrochloric acid is a strong acid, it completely dissociates into hydrogen ions and chloride ions. This means that the concentration of hydrochloric acid is equal to the concentration of hydrogen ions. The hydrogen ion concentration is given by 10 to the power of negative pH. Therefore, for a pH of 1.50, the concentration of the dilute acid is 10 to the power of negative 1.50, which equals 0.0316 moles per cubic decimeter. As the rate of reaction is a first order of hydrochloric acid, we know that the rate is equal to a constant multiplied by the concentration of hydrochloric acid. We have at least 2 approaches. The first approach is to calculate the value of the constant using the concentration from the initial analysis. This gives a constant equal to 1.4 times 10 to the power of minus 3. Next, we calculate the reaction rate for the diluted acid by substituting this constant value and the acid concentration into the equation. This gives a rate of 4.424 times 10 to the power of minus 4. In the second approach, the first rate is 9.52 times 10 to the minus 4, and this is equal to K multiplied by 0.680. The second rate is equal to K multiplied by 0.0316. Next, we divide the first rate by the second rate. Since both expressions contain K, the K values cancel out. We are left with 9.52 times 10 to the minus 4 divided by rate 2 equals 0.680 divided by 0.0316. Finally, solving for rate 2 gives 4.424 times 10 to the minus 5. In part C of question 2, we look at the reaction between the benzonediazonium ion and water to form phenol. This reaction takes place in 3 steps. Step 1, nitrogen gas is eliminated, forming a carbocation. Step 2, water acts as a nucleophile and attacks the carbocation. Step 3, a proton is lost, forming the final organic product. We are asked to complete the intermediates and add the curly arrows to show the mechanism for the reaction. In the first step, nitrogen is eliminated to form a carbocation. The pair of electrons in the bond between the nitrogen group and the carbon moves on to the nitrogen. Our first curly arrow goes from that bond to the nitrogen, producing a phenyl cation and a molecule of nitrogen gas. In the second step, one of the lone pairs on the oxygen atom of water attacks the phenyl cation. This forms the phenyloxonium ion, which we place in the second box. The next curly arrow goes from the hydrogen-oxygen bond in this ion back to the oxygen atom. This releases a proton and forms phenol in the third step. In question 3, we are given the structure of an organic intermediate, called compound A. We are asked to describe the type of stereoisomerism shown in the compound and suggest 3 reactions of compound A, one for each of the 3 functional groups using reagents of our choice. In our answer, we need to show stereoisomers of compound A, our chosen reactants and conditions, and the structures for the organic products produced. Mechanisms and equations are not required. The stereoisomer in compound A is caused by a chiral carbon, a carbon atom bonded to 4 completely different groups. First, we draw the 3-dimensional structure of compound A around the chiral carbon. Next, we create its mirror image, as though the structure were reflected in a mirror. For the reactions, we have 3 different functional groups, a keton, a nitrile group, and a hydroxymethyl group. Since no restrictions are given on which reactions to choose, I will select 3 examples. You could choose different reactions instead, and as long as they are part of the curriculum, they would also be acceptable. For the keton group, I have chosen reduction using sodium borohydride in aqueous solution at room temperature, producing a secondary alcohol. For the reaction of the nitrile group, I use dilute hydrochloric acid as the reagent and heat the mixture under reflux to produce a carboxylic acid group. For the reaction of the alcohol group, I use potassium dichromate with sulfuric acid and heat under reflux to produce a carboxylic acid. Question 4 is about Tutor salts, which are double salts with the general formula X2YZO4, 2, 6H2O. A Tutor salt contains 2 cations, X+ and Y2+. The X+ ion can be a group 1 ion such as potassium, rubidium, cesium, or francium, or it can be an ammonium ion. The Y2+ ion can be magnesium or a 2+ ion from most of the transition elements in period 4. Z can be either sulfur or chromium. An example of a Tutor salt is ammonium copper sulfate hexahydrate, NH4, 2CuSO4, 2, 6H2O. In Part A, we are asked to predict the formula of a Tutor salt that contains different ions from those in ammonium copper sulfate. In the formula for ammonium copper sulfate hexahydrate, we can replace the X+ ion, the ammonium ion, with potassium, rubidium, cesium, or francium. I will choose potassium, although any of the four options would be acceptable. For the Y2+ ion, we can replace copper with magnesium or with a 2+ ion from a period for transition element. I will choose magnesium. For the Z ion, we are told the options are sulfur or chromium. Since sulfur is already used in the original compound, we choose chromium instead. So, my final answer is K2MgCrO4, 6H2O. In question 4b, a student prepares a sample of Tutor salt in 3 steps. In step 1, the student dissolves 0.025 moles of ammonium sulfate and 0.025 moles of hydrated copper-2 sulfate pentahydrate in water, then makes the solution up to 50 cubic centimeters. In step 2, the student boils the resulting mixture for 2 minutes and then allows it to cool. In step 3, the solvent is slowly evaporated, forming pale blue crystals of Tutor salt. In the first question, we are asked what masses are needed of ammonium sulfate and copper-2 sulfate pentahydrate. To calculate these, we multiply the number of moles given by their relative formula mass. The relative molecular mass of the ammonium sulfate is 128.1, that multiply by 0.025, we obtain 3.2025 grams. The relative molecular mass of the copper-2 sulfate pentahydrate is 249.6, that multiplied by 0.025 gives 6.24 grams. In the second question, we are asked why the student allows the solvent to evaporate in step 3, instead of boiling it all off in step 2. The reason is that the required Tutor salt is hydrated. If we boil off all the solvent, the sample will lose its water. This dehydrates the sample and forms an anhydrous salt instead. In question 4c, the student dissolves their Tutor salt in water, forming a pale blue solution. The student then carries out 2 tests on this aqueous solution. In the first test, excess aqueous ammonia is added to the solution. A deep blue solution forms. We are told that the complex ion responsible for this deep blue color has a molar mass of 167.5 grams per mole, and we are asked to suggest its formula. From Part B, we know that the student's Tutor salt is ammonium copper-2 sulfate hexahydrate. The ions present are ammonium ions, copper-2 ions, and sulfate ions. Of these ions, only copper-2 ions produce blue-colored solutions in water, so we can deduce that the deep blue complex must contain copper-2. In excess aqueous ammonia, the copper-2 ion forms a complex with 4 ammonia molecules and 2 water molecules. This complex is responsible for the characteristic deep blue color. If we calculate the relative formula mass of this complex ion, we obtain 167.5 grams per mole, which matches the value given in the question. Therefore, the complex ion is made up of 1 copper ion, 4 ammonia molecules, and 2 water molecules. Remember to include the overall 2 positive charge. In the second test, the student adds aqueous sodium hydroxide to the aqueous solution of Tutor salt and then warms the mixture. A precipitate and a gas are formed. We are asked to write the formulae of the precipitate and the gas, and then suggest a test to confirm the identity of the gas. When aqueous sodium hydroxide is added to a solution containing copper-2 ions, a pale blue precipitate of copper-2 hydroxide is formed. Since the question asks for the formula, we write CuOH2. Remember that copper-2 hydroxide is insoluble in sodium hydroxide solution. However, if aqueous ammonia is used instead, an excess of ammonia dissolves the precipitate by forming copper-ammonia complexes, as seen in the first test. The ammonium ions also react with sodium hydroxide. Upon warming, ammonia gas is released. Therefore, the gas formed is NH3. To confirm the identity of the gas, hold damp red litmus paper in the fumes. Ammonia is alkaline, so it will turn the damp red litmus paper blue. In the final question, we are asked how the student could carry out a test tube test to confirm the identity of the anion present in the Tutor salt. From the previous parts, we know that the anion is the sulfate ion. Sulfate ions can be identified by adding a solution containing barium ions. If sulfate ions are present, a white precipitate of barium sulfate is formed. Therefore, for the first mark, we state that a barium salt, such as barium chloride or barium nitrate, is added. Alternatively, we can simply say that barium ions are added. For the second mark, we state the observation that a white precipitate is formed. Question 5 is about aspirin, and its structure is provided. In Part A, a student uses the reaction between aspirin and cold aqueous sodium hydroxide to determine the mass of aspirin in one tablet. We are told that, under these conditions, 1 mole of aspirin reacts with 1 mole of sodium hydroxide. The student follows the following method. In step 1, 3 aspirin tablets are reacted with 100 cubic centimeters of 0.5 moles per cubic decimeter sodium hydroxide solution. The sodium hydroxide is present in excess, and a colorless solution is formed. In step 2, the colorless solution is diluted with distilled water and made up to a total volume of 250 cubic centimeters. In step 3, a 25 cubic centimeter sample of this diluted solution is titrated with 0.2 moles per cubic decimeter hydrochloric acid placed in the burette. The hydrochloric acid reacts with the excess sodium hydroxide remaining after the reaction with aspirin according to the provided reaction. The student repeats the titration until concordant or consistent titers are obtained. A table of burette readings is provided, recorded to the nearest 0.05 cubic centimeters. From the titration results, the student can determine the following. First, the amount, in moles, of excess sodium hydroxide remaining after the aspirin has reacted. Second, the amount, in moles, of sodium hydroxide that reacted with the aspirin. We are then asked to use the titration results to determine the mass of aspirin, in milligrams, contained in 1 aspirin tablet. We are given an unknown mass of aspirin. To find it, we react the aspirin with a known amount of sodium hydroxide that is added in excess. This ensures that all of the aspirin reacts completely, leaving some sodium hydroxide unreacted. We then determine how much sodium hydroxide is left by titrating it with hydrochloric acid. From the titration results, we can calculate the amount of excess sodium hydroxide remaining. Since we know the amount of sodium hydroxide we started with, we can work out how much reacted with the aspirin. First, we calculate the titer volume by subtracting the initial burette reading from the final burette reading. This gives a titer volume of 23.10 cubic centimeters for the first reading, 22.30 cubic centimeters for the second reading, and 22.40 cubic centimeters for the third reading. To be considered concordant, the results must be within 0.1 cubic centimeter of each other. Since the first reading differs too much from the other two, we discard it. We then take the average of the second and third readings. The average of 22.30 and 22.40 cubic centimeters is 22.35 cubic centimeters. Therefore, the titer volume is 22.35 cubic centimeters. Since the concentration of hydrochloric acid is 0.2 moles per cubic decimeter, we convert the volume of 22.35 cubic centimeters into cubic decimeters and multiply this by the concentration to find the amount of hydrochloric acid used. This gives a titer of 4.47 by 10 to the power of -3 moles. Because hydrochloric acid and sodium hydroxide react in a 1:1 molar ratio, the amount of sodium hydroxide neutralized is also 4.47 by 10 to the power of -3 moles. However, these moles of sodium hydroxide came from only 25 cubic centimeters of solution, whereas the original solution volume was 250 cubic centimeters. Therefore, we multiply the number of moles by 10, giving 4.47 times 10 to the power of -2 moles of sodium hydroxide in the original solution. We initially added 100 cubic centimeters of 0.5 moles per cubic decimeter sodium hydroxide solution. This corresponds to 0.05 moles of sodium hydroxide added. Subtracting the 4.47 by 10 to the power of -2 moles of sodium hydroxide remaining from the 0.05 moles originally added gives 5.3 by 10 to the power of 3 moles. Therefore, the number of moles of sodium hydroxide neutralized by the 3 aspirin tablets is 5.3 times 10 to the power of -3 moles. As 1 mole of aspirin reacts with 1 mole of sodium hydroxide, if we have 5.3 times 10 to the power of -3 moles of sodium hydroxide, we also have 5.3 times 10 to the power of -3 moles of aspirin. To calculate the molecular mass of aspirin, I redraw the skeletal formula as a displayed formula because it makes the atoms easier to count. If you are comfortable working directly from the skeletal formula, you can count the atoms there instead. I find 9 carbon atoms, 8 hydrogen atoms, and 4 oxygen atoms. Using these numbers, the molecular mass of aspirin is 180 grams per mole. Therefore, 5.3 times 10 to the power of -3 moles of aspirin has a mass of 0.954 grams. Since this mass came from 3 aspirin tablets, the mass of 1 tablet is 0.318 grams, which is equal to 318 milligrams. The answer is 318 milligrams. Part B of question 5 contains 2 questions. In the first question, we are asked to draw a suitable apparatus for reflux. I have copied the answer shown in the mark scheme. The reflux apparatus consists of 2 main pieces of equipment, a pear-shaped flask, or a round-bottom flask, and a Liebig condenser. Make sure that the flask is clearly labeled as either pear-shaped or round-bottom. These flasks allow even heating and reduce the risk of thermal stress, which helps prevent the glass from cracking. A pear-shaped flask also directs the liquid into a small pool at the bottom, making it easier to collect every last drop with a pipette or syringe and reducing product loss. Another important point is to show the direction of the cooling water. Water should enter at the bottom of the condenser and leave at the top. This ensures that the water jacket remains completely full, giving the most efficient cooling. Finally, never seal the top of the condenser. The top must remain open to the atmosphere. If the apparatus were sealed, pressure would build up as the air and vapors inside are heated. This increase in pressure could cause the apparatus to burst or explode. For the second question in Part B, we are told that 1 mole of aspirin reacts with 3 moles of hot sodium hydroxide solution. We need to complete the equation for this reaction, showing the structures of the organic products. Aspirin contains 2 important functional groups, a carboxylic acid group and an ester group. First, the carboxylic acid group reacts with sodium hydroxide to form its sodium salt and water. Next, the ester group is hydrolyzed by the hot sodium hydroxide. This produces ethanoic acid and a phenol-derived compound. The ethanoic acid then reacts with sodium hydroxide to form sodium ethanoate and water. The phenol-derived compound is also a weak acid, so it reacts with sodium hydroxide to form its sodium salt and water. Overall, 3 moles of sodium hydroxide are used. The products are 3 molecules of water, sodium ethanoate, and the disodium salt of the benzene-derived compound. Therefore, the completed equation is as shown. Question 6 is about nitric acid, hydrochloric acid, and sulfuric acid. In Part A, we are given the structure of nitric acid, which contains 2 single covalent bonds, 1 double covalent bond, and 1 dative covalent bond. We are asked to predict the hydrogen-oxygen, nitrogen and oxygen-nitrogen-oxygen bond angles and explain our reasoning. First, consider the hydrogen-oxygen-nitrogen bond angle. This angle is similar to the bond angle in water. The oxygen atom forms 2 covalent bonds and has 2 lone pairs of electrons. This gives a tetrahedral arrangement of electron pairs around the oxygen atom. In an ideal tetrahedron, the bond angle would be 109.5 degrees. However, lone pairs repel more strongly than bonding pairs, so they push the hydrogen and nitrogen atoms closer together. As a result, the bond angle is reduced to about 104.5 degrees. Next, consider the oxygen-nitrogen-oxygen bond angle. The nitrogen atom has 3 regions of bonding electron density and no lone pairs. These 3 electron regions arrange themselves as far apart as possible, producing a trigonal planar geometry. In a trigonal planar arrangement, the bond angle is 120 degrees. Therefore, the hydrogen-oxygen-nitrogen bond angle is approximately 104.5 degrees, and the oxygen-nitrogen-oxygen bond angle is 120 degrees. In Part B of Question 6, we are looking at the reaction between dilute nitric acid and aluminium oxide to form aluminium nitrate. The first question asks us to write the balanced equation for the reaction. We are given the reactants, nitric acid and aluminium oxide. We are also told that one of the products is aluminium nitrate. At this point, we can see that the hydrogen from the nitric acid and some of the oxygen from the aluminium oxide are not accounted for in the product aluminium nitrate. This suggests that water is the second product. Another way to identify the products is to recognize that this is an acid-base reaction. Acid-base reactions produce a salt and water. Aluminium oxide is an amphoteric oxide, which means it can react as either an acid or a base. In this reaction, it reacts with the acid to form aluminium nitrate and water. Now let's balance the equation. Start by placing a 1 in front of aluminium oxide. This gives us 2 aluminium atoms on the left-hand side. To balance the aluminium atoms, place a 2 in front of aluminium nitrate. We now have 2 aluminium atoms on both sides. Next, look at the nitrate ions. There are 2 aluminium nitrate molecules on the right, giving a total of 6 nitrate ions. Therefore, we need 6 nitric acid molecules on the left. Finally, check the hydrogen and oxygen atoms. The 6 nitric acid molecules provide 6 hydrogen atoms. Together with the remaining oxygen atoms, these form 3 water molecules. The balanced equation is 6 molecules of nitric acid react with 1 formula unit of aluminium oxide to produce 2 formula units of aluminium nitrate and 3 molecules of water. In the second question, we are asked to draw a dot and cross diagram for the nitrate ion, using a different symbol to represent the extra electron. The structure of nitric acid given in Part A provides a useful clue. We expect a nitrogen atom bonded to 3 oxygen atoms, 1 oxygen with a negative charge connected by a single bond, 1 oxygen connected by a double bond, and a third oxygen connected through a dative bond from the nitrogen. To make the diagram easier to construct, I first arrange the atoms and electrons in a way that clearly shows how the final structure will form. Nitrogen has 5 valence electrons, which I represent as blue dots. Each oxygen has 6 valence electrons, which I represent as red crosses. Because nitrate is an ion with an extra electron, I add 1 additional electron, shown as a purple square, to one of the oxygen atoms. Starting with the oxygen on the right-hand side, we know there will be a dative bond. Therefore, 2 electrons from the nitrogen are used to form this bond. Next, consider the oxygen at the top left. Here, we form a single bond using 1 electron from the oxygen and 1 electron from the nitrogen. Finally, the oxygen at the bottom left forms a double bond with the nitrogen. This bond consists of two shared pairs of electrons, 2 electrons from the oxygen and 2 from the nitrogen. Putting everything together gives the required dot and cross diagram. The additional electron, shown as a purple square, can be placed on the oxygen atom that carries the negative charge or in the bond between the nitrogen and the oxygen. As an additional point, beyond the requirements of this exam question, all 3 nitrogen-oxygen bonds in the nitrate ion are actually the same length. This is because the bonding electrons are delocalized across all 3 nitrogen-oxygen bonds, rather than being confined to specific single or double bonds. For Part C of Question 6, we are dealing with aqua regia, a mixture of concentrated nitric acid and concentrated hydrochloric acid. Aqua regia is able to dissolve gold. The reaction between aqua regia and gold is a redox reaction that produces tetrachloroaurate 3 ions. In the first part of the question, we are asked to balance the oxidation half equation. We have one gold atom on the left-hand side and one tetrachloroaurate 3 ion on the right-hand side. We start with the chlorine atoms. The tetrachloroaurate 3 ion contains 4 chlorine atoms, and these come from hydrochloric acid. Therefore, we need 4 molecules of hydrochloric acid on the left-hand side. Next, we balance the hydrogen atoms. The 4 hydrochloric acid molecules provide 4 hydrogen atoms on the left-hand side. To balance these, we add 4 hydrogen ions to the right-hand side. Finally, we balance the charges. The left-hand side has an overall charge of 0. On the right-hand side, the 4 hydrogen ions contribute a total charge of +4 and the tetrachloroaurate ion has a charge of -1. This gives an overall charge of +3 on the right-hand side. To balance the charge, we add 3 electrons to the right-hand side. The equation is now fully balanced for both atoms and charge. For the second part of the question, we are told that, during the reduction process, nitric acid reacts with hydrogen ions to form 2 oxides, X and Z, with relative molecular masses of 30 and 18 respectively. We need to determine the identities of X and Z and then write the reduction half equation. As we have nitric acid and hydrogen ions, the atoms involved in the reaction are hydrogen, oxygen, and nitrogen. Using their relative atomic masses, hydrogen equals 1, oxygen equals 16, and nitrogen equals 14, we can work out the identities of the compounds. For X, the only oxide with a relative molecular mass of 30 is nitrogen monoxide. For Z, the only oxide with a relative molecular mass of 18 is water, which can be considered hydrogen oxide. Therefore, X is nitrogen monoxide and Z is water. Now we can write the reduction half equation. We begin by writing the substances involved. Nitric acid reacts with hydrogen ions to produce nitrogen monoxide and water. Since this is a reduction reaction, electrons will appear on the left-hand side. We can add them now or leave them until the charge balancing step. First, we place one nitric acid molecule on the left-hand side. Next, we balance the nitrogen atoms. There is one nitrogen atom in nitric acid, so we place one nitrogen monoxide molecule on the right-hand side. Now we balance the oxygen atoms. Nitric acid contains 3 oxygen atoms. Nitrogen monoxide contains 1 oxygen atom, so we need 2 more oxygen atoms on the right-hand side. These are supplied by adding 2 water molecules. Next, we balance the hydrogen atoms. On the right-hand side, the 2 water molecules contain 4 hydrogen atoms. On the left-hand side, nitric acid provides 1 hydrogen atom, so we need 3 more hydrogen atoms. We add 3 hydrogen ions to the left-hand side. Finally, we balance the charges. The right-hand side is neutral overall. On the left-hand side, the 3 hydrogen ions contribute a charge of +3. To balance this, we add 3 electrons to the left-hand side. The half equation is now fully balanced for both atoms and charge. In Part D of Question 6, we are given one stage of the contact process that involves the equilibrium between sulfur dioxide, oxygen, and sulfur trioxide. This equilibrium is investigated by mixing 5.82 by 10 to the power of minus 2 moles of sulfur dioxide with 7.40 by 10 to the power of minus 2 moles of oxygen in a 2 cubic decimeter container. The container is sealed and allowed to reach equilibrium at constant temperature. At equilibrium, 5.20 times 10 to the power of minus 2 moles of sulfur trioxide is formed. We are asked to determine the equilibrium concentrations and calculate the equilibrium constant, including units. To calculate the equilibrium concentrations, we first determine the number of moles present at equilibrium using an ICE table: initial, change, and equilibrium. Initially, we have 5.82 times 10 to the power of minus 2 moles of sulfur dioxide and 7.40 times 10 to the power of minus 2 moles of oxygen. There is no sulfur trioxide present initially, so its starting amount is 0. We are told that, at equilibrium, 5.20 times 10 to the power of minus 2 moles of sulfur trioxide have been formed. Therefore, the change in sulfur trioxide is plus 5.20 times 10 to the power of minus 2 moles. From the balanced equation, 2 moles of sulfur dioxide produce 2 moles of sulfur trioxide. Therefore, producing 5.20 times 10 to the power of minus 2 moles of sulfur trioxide require 5.20 times 10 to the power of minus 2 moles of sulfur dioxide to be consumed. Since sulfur dioxide is a reactant, its change is negative 5.20 times 10 to the power of minus 2 moles. Therefore, the number of moles of sulfur dioxide at equilibrium is 5.82 times 10 to the power of minus 2 minus 5.20 times 10 to the power of minus 2, giving 6.20 times 10 to the power of minus 3 moles. From the balanced equation, we also have that 1 mole of oxygen produces 2 moles of sulfur trioxide. Therefore, producing 5.20 times 10 to the power of minus 2 moles of sulfur trioxide require 2.60 times 10 to the power of minus 2 moles of oxygen to be consumed. Since oxygen is a reactant, its change is negative 2.60 times 10 to the power of minus 2 moles. Therefore, the number of moles of oxygen at equilibrium is 7.40 times 10 to the power of minus 2 minus 2.60 times 10 to the power of minus 2, giving 4.80 times 10 to the power of minus 2 moles. With the number of moles in equilibrium, we can calculate their concentrations by dividing them by the 2 cubic decimeters of the container. This gives us that the concentration in equilibrium of sulfur dioxide is 3.10 by 10 to the power of minus 3, for the oxygen 2.40 times 10 to the power of minus 2 and for the sulfur trioxide 2.60 times 10 to the power of minus 2. If we use these figures in the equilibrium constant, we get a value of 2,931. To find the units, we replace these in the equilibrium constant and cancel common terms, getting cubic decimeters divided by moles. In Part E of Question 6, we are given 3 reactions involving sulfuric acid. We are asked to identify 3 compounds formed in each of these reactions, showing structures for any organic compounds. In Reaction 1, we have that dilute sulfuric acid is reacted with nickel 2 hydroxide to form a green solution. The solvent is allowed to evaporate, leaving hydrated crystals of compound D, and we are given the percentage composition by mass of these crystals, containing nickel, sulfur, oxygen, and hydrogen. As the nickel hydroxide is a base and the sulfuric acid is an acid, we can expect an acid-base reaction to form salt and water. A reasonable prediction is that the salt formed is nickel 2 sulfate, since the metal ion comes from nickel hydroxide and the sulfate ion comes from sulfuric acid. We need to account for some hydration water because the salt is hydrated. We can calculate the empirical formula by creating a table with the atomic mass of each element. If we assume we have 100 grams of the compound, the percentages can then be treated as masses in grams. Divide each mass by the relative atomic mass of the element to find the number of moles. This gives us 0.38 moles of nickel and sulfur, 3.80 of oxygen and 4.60 of hydrogen. We identify the smaller number of moles, that it is 0.38, and calculate the number of atoms in the empirical formula by dividing the number of moles by this number. This gives us 1 mole of nickel, 1 mole of sulfur, 10 moles of oxygen and 12 moles of hydrogen, so our empirical formula is NiSO10H12. This answer is accepted by the mark scheme. However, we can go one step further. Since we expected the salt to be nickel sulfate, we can separate the formula into nickel sulfate and water. Nickel sulfate is NiSO4. That leaves O6H12. O6H12 is equivalent to 6H2O molecules. So, the formula can be written as NiSO4.6H2O. Therefore, compound D is nickel 2-sulfate hexahydrate. The overall reaction is nickel 2 hydroxide plus sulfuric acid gives nickel 2-sulfate hexahydrate. We need to adjust for the water. The neutralization reaction itself produces 2 molecules of water. However, the product contains 6 water molecules as water of crystallization. Therefore, we need for additional water molecules on the reactant side. Then, the overall reaction is nickel 2 hydroxide plus sulfuric acid and 4 water gives nickel 2 sulfate hexahydrate. In reaction 2, concentrated sulfuric acid reacts with hydrogen bromide to form 3 products, an element that exists as diatomic molecules, a gaseous compound E, and a liquid. At room temperature and pressure, 1 cubic decimeter of compound E has a mass of 2.67 grams. We need to identify compound E and write the equation for the reaction. In the presence of concentrated sulfuric acid, bromide acts as a reducing agent that is strong enough to reduce sulfate ions to sulfur dioxide. At the same time, bromide is oxidized to bromine, and water is formed. The mass of 1 cubic decimeter of gas E at room temperature and pressure can help us confirm that compound E is sulfur dioxide. Since 1 mole of any gas occupies 24 cubic decimeters under these conditions, 1 cubic decimeter of gas E corresponds to 0.0417 moles. If we divide 2.67 grams by 0.0417 moles, we obtain a molar mass of approximately 64 grams per mole. This matches the molar mass of sulfur dioxide, confirming that compound E is sulfur dioxide. To balance the equation, we could use half equations. However, in this case, we can balance it directly by inspection. First, we balance sulfur by placing 1 sulfuric acid molecule on the left and 1 sulfur dioxide molecule on the right. Next, bromine appears as molecular on the right, so we place 2 molecules of hydrogen bromide on the left to provide the 2 bromine atoms required. We then balance hydrogen and oxygen. On the left, there are 2 hydrogen atoms from the 2 hydrogen bromide molecules and 2 more from sulfuric acid, giving a total of 4 hydrogen atoms. On the right, hydrogen is present in water, so we add 2 water molecules. This accounts for all 4 hydrogen atoms. Finally, we check the oxygen atoms. On the left, sulfuric acid contains 4 oxygen atoms. On the right, sulfur dioxide contains 2 oxygen atoms, and the 2 water molecules contain 2 more oxygen atoms, giving a total of 4 oxygen atoms. Therefore, oxygen is balanced as well. The balanced equation is 2 moles of hydrogen bromide react with 1 mole of sulfuric acid to form 1 mole of sulfur dioxide, 1 mole of bromine, and 2 moles of water. Therefore, compound E is sulfur dioxide. In reaction 3, concentrated sulfuric acid acts as a catalyst when 2-hydroxypropanoic acid reacts to form compound F, which has a relative molecular mass of 144. The reaction shows that 2 moles of 2-hydroxypropanoic acid produce 1 mole of compound F and 2 moles of water. The molecular formula of 2-hydroxypropanoic acid is C3H6O3. When 2 of these molecules combine and 2 molecules of water are removed, compound F becomes C6H8O4. This formula gives a relative molecular mass of 144, which matches the information in the question. To identify possible structures for compound F, we need to consider reactions of 2-hydroxypropanoic acid that eliminate water. The molecule contains both a carboxylic acid group and a hydroxyl group. One possibility is that 2 molecules react together to form an ester linkage between the carboxylic acid group of one molecule and the hydroxyl group of the other. This produces water as a byproduct. I also show the structure given in the mark scheme. A second possibility is that one hydroxyl group is removed by dehydration to form a carbon-carbon double bond. At the same time, the carboxylic acid group reacts with the hydroxyl group of another 2-hydroxypropanoic acid molecule to form an ester. This is also accepted by the mark scheme. The mark scheme allows 2 additional structures. Although these are less likely, they are still consistent with the information provided. In the third possibility, dehydration forms an alkene, while the 2 carboxylic acid groups combine to form an acid anhydride. The fourth possibility is even less likely. In this structure, the 2 carboxylic acid groups form an acid anhydride, and the 2 hydroxyl groups combine to form an ether linkage. So, overall, the reaction involves 2 molecules of 2-hydroxypropanoic acid forming compound F and 2 molecules of water. Compound F could be any of the marked structures. Before we finish, if you found this video helpful, please click the like button and consider leaving a comment below. It really helps the channel and lets me know what kind of content you'd like to see in future videos. I've also included a link to my website in the pinned comment. If you're looking for a chemistry tutor and would like some extra support with your studies, feel free to take a look. Thanks for watching, and I'll see you in the next video.